And in the next 1 hour, as I talk, probably if you all find something challenging, stop me there. Or I can give about, I'll keep about 10-15 minutes at the end of the time. Are you all fixed on 1 hour, or do you all have a 10 minutes to spare?
We are flexible, sir, as long as you are.
Okay, I should be fine. So after the 1 hour, I will be open for discussions and question and answers, and I will try my best to answer it as much as possible. Okay, so let's go on. A small brief of my life history here. I've been in the drilling industry for about over 30 years, did oil and gas for about 12 years, was mainly based out of Indonesia, did a little bit in India before that, and then for about 10 years was based in Jakarta, Indonesia. I used to be specialized in drilling offshore, high pressure, high temperature oil and gas wells. One of the rigs that I used to work a long time was on the Deepwater Discovery. And if you guys are familiar, because you are from the drilling industry, how many of you all have seen the movie called Deepwater Horizon? Have you all seen it?
Yes.
Okay.
Yes.
I used to be working on one of her sister rigs. So there are 4 of them in the world. I used to be working on one of the sisters of that, Deepwater Horizon. It was Deepwater Discovery for about 7 years. Pretty challenging environment, but used to enjoy the challenges because that's what makes life more worthwhile. Otherwise, you go to and why I picked up petroleum or drilling industry was that I got bored of wanting to go and sit behind a desk and write some things every day and go back home at 5 o'clock in the evening. Rather than that, I prefer this more challenging. And what it has helped me is that it has helped me to travel the world. Let me tell you that. So if you see on this slide here, you see a small splattering of what I do. So right on can you see my cursor?
Yes, sir.
Okay, so that picture that you're seeing there is actually a picture taken at the African Union seat of African Union in Addis Ababa in Ethiopia. African Union represents 55 countries in Africa. So what happened there was they used to not have much of rules and regulations for drilling anywhere. So we actually got together as a team and prepared the rules and regulations. And this is in about 2016, where I am opening the session for the African Union and presenting the rules and regulations to the energy ministers of the 55 countries in Africa. And that has now become actually a law in a few countries and is being adopted now in more countries. The next slide, next picture that you see is actually one of the things is a power plant in Kenya, where that power plant generates about 110 megawatts of power. And for those of you all who are not used to that, 1 megawatt of power in the US terms will power about 3,000 houses. So you can think that that's about 300,000 houses can be powered by that one geothermal power plant. On the next one here is actually an outward view of one of the biggest geothermal projects in the world. This is in Kenya. And for those of you who are interested to learn a little bit more, this is the only geothermal project in the world that sits right in the middle of a national park. So the animals have the first right of way when I'm driving through that place. If a giraffe crosses my road, I have to wait, give him way, and then I continue on. But that is one of the best places that I've drilled in the world. Then next to that over here is one of the first wells that was ever drilled on the island of Dominica. This is in the Caribbean islands. And it was pretty challenging because we had to make new roads and all to go there. That's why I wanted to just put that up. Now, down here, you see is the biggest geothermal well in the world as we speak currently. It sits in Southern California. That one well generates 50 megawatts of power, 50. And this is I do also a lot of training for the International Geothermal Association. So here is a training that we were holding for a whole team that came from Kenya, from Kenyan, to actually see how we do operations in the US. Next to that is here is a project that we did on the big island of Hawaii, where we did one of the deepest foam cement jobs. I'll come to that later, but just keep that. This is one of the most, again, interesting places. Here on this place, you are actually sitting about 11 miles crow flying distance from the Kilauea volcano. And if you are aware of that, that is a volcano that's been flowing since 1984. It flows from the top of Mount Kilauea, flows into the ocean. Last of it, the picture here is, I also do some of the planning for these wells. And here we are up in Colombia at about 3,000 meters height, or about 12,000 feet. We are actually in the Volcano del Ruiz, and we are actually planning on a new well site over there for putting up a new power plant. So this is sort of what I do in terms of oil and gas and geothermal now, especially. And this is why I enjoy what I do. Now, to start off with, why more coming on to the topic that we are discussing today, what we are trying to understand is, why is geothermal important? One, what are the various types of geothermal projects that are going on currently? Where are geothermal sites normally located? Then I wanted to just talk a little bit more detailed about what is the comparison and difference that you find between oil and gas and geothermal. Plus, can oil and gas technology be applied to geothermal? That is the biggest question. And while we are here, I'll just touch on that. So most of the technologies that we currently have in geothermal are actually taken from oil and gas. So we lag behind a little bit in oil and gas, but most of the technology is taken from there. One of the challenges that we have sometimes with oil and gas compared to geothermal, or geothermal compared to oil and gas, is that geothermal wells have a higher temperature, number one. So your higher temperature, so most of your example directional drilling tools have a certain limitation of temperature that you use in oil and gas. They cannot be used in geothermal as they are. So you have to sometimes do a little bit of modification to use the oil and gas tools in the geothermal. Then the geothermal environment as a whole is pretty challenging compared to oil and gas. One of the things what I wanted to show is that some of the places that you drill in the world, you are sitting very close to human habitations or towns. Then some of the places are in very pristine environments. So there again, it becomes a question of how do you harness your resource that is down below, number one. Then how do you make the best use of it? And what are the uses that you have? For example, if you see on that picture down below, this is a picture from the Blue Lagoon in Iceland. So what you have in the background, if you see over there, is the power plant that generates power. And the fluid that comes out from there is actually fed into this geothermal spa, which has become now a big, it's one of the most touristy attractions on your Icelandic tour map. Same thing happens in Kenya. We've got a very similar setup there, where if you all ever get a chance to go to Kenya, you will normally hear about Masai Mara. Have you heard of that place? Masai Mara is one of the biggest national parks in the world, and if you all are used to that, you will see a big wildebeest migration in Kenya. That's actually where it sits. And as a part of that, now geothermal is again becoming a big part of the Kenyan energy space. So they want to become more like green energy. And I will touch upon that later when we come to that spot. Any questions at this point so far?
No, sir, we can continue.
Okay. Now, wanted to give you a small idea. I'm sure you all might have already seen the slides a couple of times during your courses. But here is what we sit around. Where is the geothermal generally spotted around in the world? We normally find them all along the tectonic plates and tectonic boundaries, as well as some of the volcanic regions of the world. Some places you've got both together. For example, New Zealand has both. It sits on the tectonic plate. If you see here down below, it sits on the tectonic plate, as well as there are many active volcanoes over there. Compared to that, if you think of This is the Salton Sea area or just on the Mexican border. This area does not have much of volcanic activity, but it's a very important tectonic plate in the world. That is why if you, for example, where I'm sitting and speaking to you all, I live in southern part of California in a small place called La Quinta. We are about 15 miles away from the San Andreas Fault. I'm sure you all have heard of that, right?
Yes.
Yes, sir.
So the San Andreas Fault where you're sitting, we do, here we sit and we expect, we are happy that once in a way we get a 3, 4, or 5 megawatt magnitude earthquake. We are very happy that, okay, the big one is far away. If not, that's what it is building up to. So that's what happens again in places like Indonesia. Indonesia, that's sitting over here, one of the biggest producers in the world, along with Philippines, sits on both. It sits on a tectonic plate where there's a subduction zone, as well as there are many active volcanoes because of the thinness of the crust of the earth. So these are the places that you will normally find geothermal. Now, this is geothermal when we talk in terms of conventional. Now, why am I talking of that? You might now have heard of a new term that is being used all around, which is called EGS, Enhanced Geothermal Systems. What are the enhanced geothermal systems called, and why are they quite important in the current context that even you all as students are preparing? Because conventional geothermal is not spread all across, and the wells are of different sizes in different parts of the world. Now, when you talk of EGS, what they are trying to do is, in places that there is not much of conventional geothermal, they are trying to drill some wells, simulate them using either injecting cold water, doing some helping the ground, which has got a little bit of permeability, to increase its permeability because of the cold fluid, and expecting the conduction of the Earth's heat to be conveyed back to the fluid that you have pumped, and you plan to extract the fluid from your production well. This is now being done a lot, and if you have been reading recently, there are companies like Ever, companies like Fervo, which is doing quite a bit of the work. And also I'm involved in a couple of projects at Forge in Utah, and some of the other projects with Berkeley Labs. What we are trying to do is, Forge is now becoming a big research facility where we are now trying to see how can we drill into granite, for example, deeper, and get whatever heat is there. You actually extract the heat using the water or the cold fluid that you're pumping and take it back to production. Now, Forge, I'll just take a few moments to speak about Forge. Forge has been a project that we have been involved, which has been doing all the things that you can imagine, like what you do at your labs in OU, trying to stretch the limits of what is currently available. For example, we are looking at directional drilling tools, which are currently rated at about 175 degrees centigrade, operational limits. We are trying to stretch that to 200. Then we are trying to look for new bits that can be used for helping to drill faster and keep the hole in shape. We are also trying to do about drilling fluids. Some of it is trying to do some optic fiber research on trying to gather data from these wells once they are producing. These are all things that are going on currently in the Forge project, and a couple of the various areas that they're drilling in. They are trying to see what Department of Energy is trying to do, is trying to see is how can we make it more cheaper? Because geothermal energy has a high startup cost, but over the time, the cost is negated because it is renewable and it's producing on its own. But there's an initial high startup cost. Now, if you see the slide here, you see that I wanted to just touch upon what we have been just talking. It is all based on the temperature of the wells that we encounter, right? So what happens there is, if you see on this graph here, you see on the left side, you see on your y-axis, you see your depth in kilometers. We are talking about 5 kilometers or roughly about 18,000 feet depth. And on the x-axis, you are seeing temperature in terms of degrees centigrade, on which they can produce, say, it's going to almost about 325 degrees centigrade, or in Fahrenheit terms, about 650 to 700 degrees Fahrenheit. Now, what you see is, what are we looking for when we look for geothermal wells? What we are looking for is, how can I get, normally your geothermal gradient, your heat gradient is fixed, but we are looking for places where the average gradient is much higher, about 25 degrees per kilometer, which is higher. That is what we are interested in when we are looking for geothermal projects. Now, if you see here, if you go from left to right, right to left over here, let me go from right to left, it's easier. So if you see around this orange place here, that's the first circle, those are flash plants. What are the flash plants? They are actually plants where the steam or hot water is extracted, and the steam is very hot at about, say, 250 to 300 degrees centigrade, which can directly go and run a power plant, a turbine in a power plant. That's the first one. So you will find they are located in places in the world which have got very high temperature in the ground at the geothermal projects. These were very commonly done quite a long time, where there were flash plants, especially flash plants in the US. You will find Nevada and some of them, the geysers down in the Salton Sea, in Hawaii. Kenya has a lot of flash plants. Indonesia has a lot of flash plants. That is because the temperature of the geothermal resource is pretty high. Now, there were some resources, a lot of resources, not some, I would say a lot of resources in the world, which are not up to this temperature in terms of temperature, but they are still in the range of about 200 to 250 degrees centigrade. Now, for a long time, many of the first producers in the world was like Italian, the Laredello project. Then there was projects in Indonesia, in the US, where people would say, oh, I do not have temperature enough to run a flash plant, so I cannot produce. So what happened? Ormat was one of the first companies that came into picture. They used, instead of using binary plants, they used, actually in a flash plant, they used a binary plant. Now, what does a binary plant mean? Here, a fluid other than the steam or the hot water is going and running a turbine and producing power. And this fluid normally used is isopentane, and that goes in the system, remains out there, and then produces power. The third part of it now comes, so this is now becoming a big place, big project owners in terms of, say, like developers who have got temperatures of between about 150 to 250 degrees centigrade. They're able to produce power using the binary plants. Now, there are a lot of projects in the world which do not have even that type of temperature. They may be about 100 degrees centigrade in temperature. Now, what would you have done with that? Nowadays, we have got technologies that can use, one is called, if you all are familiar with the term, ORC, Organic Rankine Cycle. They use temperatures lower than that, and they use almost like a refrigerating process. If you take a refrigerating setup, and where you're helping the heat transfer to cool or heat the system, the same thing is used to produce power from much lower temperatures. For example, one of the projects that is being done currently in the US, in Nevada, is by a company called Kaishan. They are one of the biggest air conditioning manufacturers in the world. So they use the same technology, did a bit of reverse engineering, and produce power out of that. But they can produce power from almost as low as 130 degrees centigrade. Now, this is now a big part. I'm sure as some of you all will go out into the world of jobs, looking for work in probably a year or two, once you finish your studies, a lot of projects are going to come in this space called enhanced geothermal systems. So what here we are doing is, as I was mentioning earlier, where there is very less terms of temperature or heat availability at a shallow depth, now they're trying to go deeper and trying to find some more hotter fluids, which may not have the real good permeability as you would expect in the geothermal, actual conventional geothermal, but they're trying to simulate that and produce power out of that. Now, here is something I just wanted to touch upon is, here you see the forecast versus well performance. So what happens is, whenever we are forecasting some projects, okay, they say, okay, Sam, can you tell me how much will this well produce? So we have not drilled the well. So like some of you guys may be geoscientists or reservoir engineers, or, so when you all are planning a well, so what you do is, or working on a project based on data that's available, including geoscience, geology, geochemistry, geophysics, some satellite imagery. Based on all that, you come up with a plan for drilling, starting on a project. This project may have, say, probably 10 megawatts. Okay. Now I'll give you a small joke to tell you all. So what happens now? Now I've got 10 megawatts. I know that this project can produce 10 megawatts. I take that to my manager, because nowadays everybody is talking of investment. When I take it to my manager says, Sam, what am I going to do with 10 megawatts? No, it's hardly anything. So what he says, oh no, we have to make it really more attractive. You all are used to the term wrapping in a golden wrapper, I'm sure. So you want to make it more attractive for the investors. So what he does, okay, I sit with, say, example, Orkan is there and he's sitting and talking with me. He says, Orkan is my manager. I tell him, hey, Orkan, I've got 10 megawatts of power. He says, no, Sam, I cannot even think of that. So he says, what do I do now? I add one more zero to that. Oh, okay. Suddenly now it became a 100 megawatt project. Yeah, it's worthwhile. There was actually only 10 megawatts, right? Now, myself and Orkan take this to a investment company somewhere in the US, a big investor. A lot of them have green money to spend. So they take it. He tells me, Sam, what is 100 megawatts? I don't want to spend my money on 100 megawatts. Now we sit and scratch our heads. Finally, he says, okay, let's do something to make it more interesting. We put one more zero to that. So what happened? Suddenly, a 10 megawatt project suddenly became a 100 megawatt project, right? And then what happens there is, now you have planned all this, right? You have not drilled your well. Now suddenly first you go and drill a well, and then you suddenly realize after drilling 2 wells, there is not more than 10 megawatts in my project. But I had got investors to invest in this, saying that there's a big project there. Now what happens? This project finally comes to a standstill, gets either stalled or goes into bankruptcy. So it becomes one of the projects on the list of projects that started, never completed, money spent. What do you get at the end of it? Nothing. This is, again, that's why I wanted to show you all this, that forecast versus well performance. I would say when somebody asks me, Sam, can you help us with this project? I would be more upfront and telling, hey, guys, there is 50 megawatts of power here. I cannot tell you there's 1,000, but I know there's 50 megawatts of power and I can make it work and it can be sustainable. That is what we should be talking about. Hope it makes sense to you. And I'm just giving you some of these tips, which once you're going to the industry in the future, these are some things to keep in mind. Now, let me go into specifically into a little bit of comparison. I'm talking first about oil and gas wells. So if you see on the right side, this is actually when I was presenting, I told you in African Union, this is now the code of practices that we have developed and is being applicable in different countries, in Africa especially. And this was actually based on the New Zealand code of practices, which I'm very familiar with and used to work with. Now, normally in oil and gas, you see that the hole sizes are smaller. Your production holes are completed in about 5.5 inch or 5-inch hole sections. That is big for them because they are looking at a lot of pressure and how can we get the fluid out in terms of oil or gas or both. Now, in oil and gas, again, we do a lot of horizontal wells where we are looking at, you are looking at drilling a section, kicking off and doing a lateral. Some of those laterals in some places like the Permian basins and all are almost 3 to 4 miles long, where they're trying to get the best out of the sand that is encountered. Okay. Then directional wells in oil and gas, we have got a lot of technology that we can use to make sure we are able to target the wells properly because they are lower in temperature. Now, the third thing in oil and gas is we use a lot of oil-based mud. Why? Because the oil-based mud helps us to drill these wells better, helps cleaning, as well as, we have made them pretty environmentally favorable, but still there is always EPA that does not want you to spill any of the oil and gas, oil-based mud on the site. Now, we also use a lot of LWD and MWD tools, which help us to target and make sure that the well path that we are taking is the best well path. Then, do you all know what is a spider plot? Have you heard of this term?
Yes, yes, sir.
Okay, so some of the wells, like for example, if you are in the Thumbs Island, just offshore in California, and some of the wells that I used to drill back in Indonesia, we used to have, it was almost like a spider web, and making sure that these wells are crisscrossing each other, but never hitting each other was the biggest challenge. Because the moment you hit something, you have asked for trouble. But that was the biggest problem that we used to have when we are drilling wells in very close proximity, almost like going here and there and making sure that these wells do not collide. Last of it is the size of the rigs. Many times the size of the rigs that we drill in oil and gas, they are based upon one is the size of the last casing that we would use, the size of the wellbore that you would drill, and the size of the drill pipe that you would use. So many times we can manage with, say, about 1,000 horsepower, 1,000 horsepower rig, 1,500 to reach to the TD. Then, because the holes are smaller, your BOPs are also smaller. What is a BOP? BOP. Have you heard this term?
Blowout preventer.
Yes, that is my last line of defense if the well comes alive. So the blowout preventers in an oil and gas well will be smaller in size compared to geothermal. And also the wellheads have a different design compared to geothermal in terms of oil and gas, because normally in oil and gas wellheads, we've got a tubing that comes up to surface, and that is through which the oil comes back to surface. Now, in geothermal, the difference is that we are looking for not mostly pressure, but we are looking for heat. Plus, our volume has to be bigger, because if you read there, the thermal efficiency of converting steam or water to electricity is only about 20%. So you need a lot of volume of water to be able to produce that power from the resource, which is either steam or hot water. So what happens? We need larger well volumes to flow, larger diameters of casing. So that is why we have to think of that when you talk of all about the well design and the equipments that will be used. Now, we also have a problem when we drill these wells in oil and gas, in geothermal compared to oil and gas. We have a lot of lost circulation. Now, if I have to give a very simple example for lost circulation, for those who are not familiar, when you're drilling, you are actually pumping, this is your drill string, where you're pumping water down your drill string. It goes out to the bit, comes through the annulus, picks up the cuttings, comes back to surface. That if that whole cycle is going properly, that means I'm having full returns. I'm pumping something, I'm getting exactly back. The well is going very well. But normally in geothermal, when we hit some big fractures or big cracks in the ground, which is because of the volcanic activity and other things, we lose circulation. So what happens? I'm pumping down the drill string, I do not get anything back. So what happens? I'm losing water or losing fluid. So because of that, I need to have a lot of water available at any given time when we are drilling a geothermal well. Also, it is used for well control. I'll come to that later. Then we normally have something called a top drive. Have you all read about a top drive on an oil and gas rig?
Yes, sir.
Okay, so what is the main advantage of a top drive? Normally, before the top drives were invented, we used to have a Kelly. So the Kelly, what it does is Kelly has a bushing that sits down below, and it goes and sits on the rotary table, and this bushing locks in place. So when the rotary table turns, the string also turns. But that string, the moment you are coming out of your well, that string will not turn once the bushing is out of the rotary table. So what happens when I'm coming out, if I want to back ream or something, I cannot use that. So that is why top drive is quite important, because it can continue circulation and rotation while I'm coming out of the hole. Last thing is, very important thing here is casing. The casings in geothermal and the casing connections are very important because one of the things keep in mind, or a difference also, how long do you expect an oil and gas well to be operational? Give me a rough estimate. How long do you expect an oil and gas well to be operational?
Around 20 years. 20 years.
Because what you're looking for is you want to drill, get the oil and gas out, and I'm happy with, if I get the oil and gas out the easiest I can finish that in about 2 or 3 years or 5 years, and happy that well is abandoned and we'll move on. Or some of them do enhanced oil recovery, where you pump some steam, get the final little bit of oil and gas that is there, get it out. Geothermal is not like that. Geothermal wells have to produce for about 25 to 30 years minimum. That is what we call is the life of a power purchase agreement. What's a power purchase agreement? So a power purchase agreement is that when I drill, I get steam out. That steam generates power. Now, what do I do with this power? I have to supply it to a transmission company, who then supplies power to you in your office. So that is what is the power purchase agreement. So there is an off-taker of your power who supplies power to the final customer and pays you for the money. These off-takers have normally signed 25 to 30-year power purchase agreements. That means you have to maintain your resource properly and be able to supply heat from your plant that generates power to your final off-taker. Like here in the US, we've got different transmission companies who supply power to you as a customer. Now, in casings, one of the problems that we have to make sure is, in geothermal wells, you have something called thermal expansion and cooling. Because what happens, as soon as I've drilled a geothermal well, my temperature is probably ambient, say 70 degrees Fahrenheit. But the moment I turn my well on, that ambient temperature from about 70 degrees Fahrenheit goes up to about 550 degrees Fahrenheit. Now, imagine what is happening to this casing that has been cemented in the well. It is certainly stainless steel or carbon steel, but it stretches. And let me tell you how much does it stretch. I was not really ready to believe it when somebody told me, till I actually had to find out. In Hawaii, the wells produce at about 575 degrees Fahrenheit in terms of temperature and about 500 psi in terms of pressure. So we had just finished drilling this well, and one of the boys told me, "Hey, Sam, tomorrow when you come to," so my drilling team finished everything, and I was just about going on because, I had some, and then they told me, "Sam, tomorrow when you come back, the well is not flowing, but the well is heating up. You will see this master valve growing. So that is the valve that is finally on top of the well on the surface." I did not believe it. He told me it'll grow about 3 feet. Next morning, we come back, and this rope that I tied down to the ground, which was about this much to the ground, had grown by about 3 feet in height. Now, if you want to get an idea of what we are talking about, is imagine, you can try this at home or in your labs. Imagine a piece of steel or carbon steel that is cemented and wants to grow and expand. What will happen to that? It's going to stretch, right? And the points are wherever you've got what you see there is the casing coupling. That's where the connections are made. That is the weakest point that's going to stretch. Now, one is it has stretched, okay? For example, it has stretched, and this well is flowing 24/7, 365 at 575 degrees Fahrenheit. Now, imagine after 1 year's time, we sometimes have to do a workover on these wells or do some clean outs. You have to cool this well down. Now what happens to that casing? The casing has expanded almost 3 feet, and then you expect it to cool down 3 feet. You are not talking of a rubber band, but here you're talking of carbon steel casing. Think of that. I'll leave it there for you all to have an imagination so that I'm not talking everything. But think of, or when you all are having these discussions, think of the amount of thermal stress that happens on the casing connection, and the cement. That is why casing our well design is quite important in geothermal wells. Now, some of the other problems that we have, challenges, okay? One is that because these wells are bigger in size, and if I'm doing directional wells, I need bigger directional drilling tools to be able to drill these wells. Now, some of these directional drilling tools, once you put a bottom hole assembly of a directional drilling tool, they are about $3 to $4 million in cost per well. Let me repeat, $3 to $4 million per string when it is run in the well. Plus, they have got a lot of elastomers or rubbers that are used for rotation and things like that, and sealing. Once they are heated up, they expand, the elastomers can get eaten away because of the heat, and problems can happen. That's number one. Number two is, normally in oil and gas wells, we build angle of about 70 to 90 degrees. Almost we go horizontal. Geothermal, we have not gone to that extent as yet. We stick around 20 to 30 degrees in direction. Plus, we have not tried horizontal. We are now trying them. Normally, before it used to be either an S-shaped well. So you actually drill, kick off, and then drop the angle. That's number one. Or you drill, kick off, and hold angle. That's the J-shaped well. Now, some of the other things there, because of the higher temperature, also geothermal wells compared to oil and gas wells. In oil and gas, normally we are drilling into sedimentary formations, which are pretty soft. Geothermal wells, even in like Hawaii, we are drilling into lava right from the surface. This is volcanic rock, which is very hard and takes time to drill. That is our biggest challenge. And we have really overcome that challenge when we are doing this project at Forge, where we were able to use PDC bits compared to roller cone and drill faster. Now, one of the things, what happens to, suppose you've got a rubber element, okay, that is sealing at, say, at 100 degrees Fahrenheit centigrade, it seals at about 10,000 psi. Now, suppose I increase the temperature to 200 degrees centigrade. What happens to the pressure? Decreases, right? Because what happens is, as the temperature increases, your pressure elements, especially rubbers, are derated. So this is a big problem that we have seen in some of the wells, because as the temperature rises up, when we try to seal something, because of increasing temperature, the pressure gets derated. Now, if you see that second last line there, what is H2S? Have you heard of this term H2S? It's a, let me give you a clue. It's a gas.
Yeah. Yes. Hydrogen sulfide.
Yes, the hydrogen sulfide gas. This is one of the gases that is a byproduct in geothermal, in a lot of the geothermal wells, and is one of the most dangerous in the world. Sam Abraham, who's talking to you, would not have been talking to you if I was not masked up fully in a project on an oil and gas well in Indonesia for ExxonMobil. We were actually doing, we had just run the RFT tool, and we were getting the RFT tool back to surface to collect the gas sample from the well. And Exxon's oil and gas well in Indonesia. We were trying to get the RFT chamber out and trying to collect the gas. Something happened, there was a leak, and I was one of the managers on that site, and I was actually fully masked up while they were doing this. We had evacuated the whole rig site. We had only 4 of us, the most important people, and 1 person from the hydrogen sulfide detection team standing with us. There, one of the requirements is that you cannot keep a beard or a mustache, because you had to have a full sealing over here with your mask. And something happened, and this gas leaked. And the person who was standing next to me had a dragger tube, and he was detecting the gas. It was over 8,000 ppm. And let me tell you one thing, 30 ppm, you can be history.
Yeah.
I was standing next to 8,000 ppm. By God's grace, just because we were fully masked up, I'm talking to you. Otherwise, that would have been history. These are some of the challenges that we face in geothermal. Plus, you see the next one, CO2, carbon dioxide. This is a very common thing in the atmosphere. But once carbon dioxide mixes with water, what happened? What is the acid that's formed? It's called carbonic acid. This acid is one of the most corrosive things in the world that you can find. For example, I'll give you, in some of the wells, we have carbon steel casing, which is about 1 inch thickness in radius, 1 inch thick, okay? You run those carbon steel casings in some of these wells that have got CO2. You come back in about a year's time, the casing becomes aluminum foil. That's what happens to the casing, and that well can be destroyed. Then the last thing out here, whenever we are doing geothermal compared to oil and gas wells, you always have to think of two types of wells. One is production wells and one is injection well. So the production well normally, just for a simple ratio, is about you drill 4 production wells and you've got 1 injection well. What that helps to do is it helps you to pump the fluid back into the ground, so it keeps the pressure high of the whole reservoir. Plus, it helps you to dispose. Now, why is this important? If you all are familiar with the geysers area in Northern California, they were a lot of time producing a lot of the steam, but they were not injecting. What happened? Gradually, their reservoir pressure started dropping down, and they had to fix that problem. So currently what they do, they actually take the wastewater that comes out from the Santa Rosa city's well, the wastewater treatment plant, and that is injected back into the ground. And that has helped to stabilize the reservoir pressure. Moving on. We did speak about this, so I won't spend much time there, but this is what we have been talking about. What is a normal geothermal well design? Here you see a surface casing right at the start. This surface casing is set so that it takes care of shallow, unconsolidated formations. Then you go down to a depth, which is about, say here, the second casing. What that takes care of is if there is any groundwater in the area, permit requirements require that you should protect the groundwater from getting contaminated. So one of the important things of this second casing is actually to protect any groundwater contamination. Third one is here. This is the most important casing in the wellbore. This is the one that is the production casing. Why do we call it production casing? If you see down below, this is a slotted liner. That's the last liner. What we do is till this point, you see this is all cemented back to surface. But this section is my production section. This is the place where I am pumping. This is where the steam or hot water starts coming in from the wellbore. It actually comes through this slotted liner, and then it flows through this production casing back up to surface. Now, on the right-hand side here, you see, why do we set the casings at particular depths? Here you see the gradient, temperature gradient in the wellbore as it's going up. You see, I try to set this last production casing before it becomes almost linear. Here you see the temperature is gradually rising up, but once you come to this point, it has a good production temperature and it stays almost steady. So that is why I set this casing before that point and make sure I've got all that behind casing. This is a very simple well design, normally a production, and we have the slotted liner. Sometimes we do not need to run slotted liners if the formation is very competent. But if it is not competent, we run the slotted liner so that only the fluid and the steam can come into the well, and the well itself, if it collapses also, will not affect the casing or affect your wellbore productivity. Now, here you see, okay, let me show you something here. Now, normally, when we are planning for drilling wells, we normally look at what are the type of rigs that I need to use. Now, these type of rigs depend, one is on the well depth that you need to drill, also sometimes on the locations. For example, this location that you're seeing here was actually in the Commonwealth of Dominica in the Caribbean islands. This was the first well ever to be drilled on that island. There were no roads. So there were roads, but very tight roads, and it was a mountainous area. So we had to use the smaller rig, which had good capacity to go deeper, but which has got a very small footprint. So we could take it up to the mountaintop, do the drilling, and then go off from there. These are the other type of rigs that we do normally. That's 1,000 horsepower to a 2,000 horsepower rig, and what we call is a triple. And these are wells that we normally rigs that we normally use. They also need to have, the diesel generators and enough of capacity to be able to pull. Now, if you see here, what do I mean by pull? It is like, if I have to give you a very simple example, if you want to say go from Oklahoma to Texas, to say Houston, and you want to go till there, you need a certain amount of fuel to go. You always like to go with a little bit of extra fuel, right? Just in case you are not stuck on the way. Same thing happens when we are planning these wells. We plan to have them, especially any of you all geologists who are listening to me.
No,
Okay.
problem engineer.
Okay, engineering guys, fine. But normally even the engineering guys would always tell me, oh, Sam, this is again, now I'm putting my hat on of a finance manager who's looking at the contract, okay? What he tells me, Orkan, how much do you want to drill? Yeah, I want to go to 5,000 feet. Then I go into the market and look for a drill that I can contract to drill to 5,000 feet. Suddenly the geologist tells me, Sam, I want to go to 5,500. Now what do I do? So that is why whenever we plan these wells, always make sure that you've got rigs that have got a little bit of additional capacity to be able to drill deeper. Now, along with that, I will give you one more tip. Some of these wells, like say in Dominica, are so remote. For example, in Hawaii, when I'm drilling, my nearest supply port for any equipment is Los Angeles. That is 14 days by ship. And the rigs, normally these drilling rigs, when they are in operation, the per day rate for a drilling rig, what do you think will it be costing? Just give me a rough estimate. Just think about it. Per day, what will it cost for doing this whole operation? Any numbers? Want to throw out something?
$100,000.
Somebody got it pretty right. That's what we have for onshore geothermal wells. We have not gone offshore as yet. Now, for example, the Deepwater Horizon that went down, that used to cost about $1 million per day rental. That is why sometimes cutting corners, people try to, hey, can I save a little bit of time by not doing something that is very essential, like a pressure test? Now, what happens out of that? Say 10,000, say 1,000 times, 999 times, it will not hurt you. You can cut a corner. But that one time it hurts you, that is what happened to Deepwater Horizon. It has happened to different rigs. I'll show you a couple of pictures. That is why we do not cut corners and do not save money on a big. Saving money can cost you your life, others' life, as well as the environment. I'm sure you all might be knowing that BP is still paying for Deepwater Horizon problem. Still paying because environmental problems are still continuing because of that. Okay. Now we come to, I did touch upon this, so I won't spend much time there. But this is, for example, just to give you an idea of a blowout preventer. So this is what we call the annular preventer. This is the one that can seal against any size of casing. These two are called rams, or we call, they close across a particular size of casing. And the last one, this one, can actually cut through pipe. Steel pipe, it can cut through. So we normally have these three things on our well at any given time, because this is my last line of defense. In case the well comes alive, I have to use this to shut the well in and keep my personal equipments and environment safe. Also, one of the things is that, I will come to that in a little bit, is that we have got very specially designed cement slurries when we are doing geothermal wells. Now, what you see the picture down below here is, after I drill a well, I've gone to TD, total depth, I've drilled the well. Before the rig goes off location, I do a very small flow test. And that is what is being done over here. So I've got the rig still standing by there. On the well, I do a small flow test to see if this well is really productive. If it is, so there you can see it is really coming up with steam back to surface. That means I know this well is good. At that point, then I do sign off that this rig can be released to go and drill a new well, and we continue testing the well. Why is this important that I just touched upon? Is because if you let the rig go and if you do the test after the rig is gone, suddenly you think the well does not flow, then you have to actually get the rig back on the well to do maybe a sidetrack or something. That's why it's quite important that we do this well flow test before we actually move off location. I've got about 10 minutes. Okay. One of the most important things in geothermal wells is that we drill these formations that we drill have got a very low fracture gradient. What is a fracture gradient? Because the fracture gradient is a plane point at which above a certain pressure that is applied to the formation will fracture and you will not get returns back to surface. So one of the most important things that we have done in geothermal wells is trying to cement those wells successfully using foam cement. So what is this foam cement? So we normally mix cement, then we mix steam along nitrogen along with that to make the cement lighter. So the cement is lighter but still has the same properties, and then we pump the cement in the wellbore. Now, one of the differences also you have to realize that happens between oil and gas wells and geothermal wells. I'll go back to that slide where we were talking about the well design. So here in oil and gas wells, if I get just about, say, till this point, say about 300-400 feet of cement around my casing shoe, I'm very happy even if this casing is empty. But in geothermal wells, our first intent is always to get cement from the casing shoe back to surface completely in the annulus. That is a very important distinction what we talk between oil and gas wells and geothermal wells. Now, quickly moving to something that's quite important. Wanted to share this with you all. Okay. Now, one of the things that we're talking about is BOP. There is well control. So if a well has a problem, I can close the BOP and I can shut the well in. Now, I want to show you all something. This is an actual photograph. You see, they were drilling over here on this site. This is a site in Eastern Europe. What happened is that as they were drilling, they did not set the casing at the plant depth. They wanted to go a little bit further. This point to this point is about 1.5 kilometers or about a mile away. This is a very rich agricultural area which produces a lot of wines for vineyards. They are drilling and suddenly they start seeing some small bubbling of water coming up, mud coming up about 1 mile away. Oh, they thought it may be something not really important. It's just something coming up from the ground. In about 3 days' time, this crack moved all across and came right onto the rig side. And you see this crack? It went down below the rig floor. They had to pull the rig off location. What had happened was that there was a crack in the ground and there was an underground blowout. And that underground blowout brought that thing back to there. Luckily, nobody died, but the rig had to be pulled out. And this area still sits like a hot steaming pool even now after 4 years. One of the other things is here, this is another picture of the same. That is the Kenyan project that I was talking about, sitting right in the middle of a national park. You can actually see zebras grazing there, and there are some other animals in the background. This is a place which I sort of think of as one of the most pristine environments where technology, nature, energy coexist together. Now, all we have been talking about here was okay. This is normally what we have called a wellhead. So after we drill a well, you saw the casings that were run. This is what you see on surface of the well when you finish drilling a geothermal well. So this is what we call, this place is called the casing head flange that sits on the last casing. This is an expansion spool. Sometimes we use that. And this is what we call a master valve that sits on top of the well. This is a very typical wellhead that you will go to any rig site after the drilling is completed. And normally from here, there is a pipeline that will be taking the steam back to the power plant. This is a very typical example. Now, we have been talking a lot about what we do with the steam. So currently, mainly our steam used to generate power. If you see on this picture here, this is the Hellishekler power plant in Iceland. So there they're generating power of almost, I think so it was 78 megawatts. Now, the geothermal has a lot more of value to that. So what happens? Once the steam goes through the turbine and flashes, it condenses. The steam that comes out is pretty hot still there, or the hot water is pretty warm. So what now we have tried to do is, we have tried to use that steam or that hot water to do a lot of things. So this, if you are an investor, that is your value addition to the various things. Now, why is this very important? You see this picture over here down below? This is one of the projects in Kenya where actually we provide the CO2 that comes out from the wells, from the geothermal brine, and the heat to heat greenhouses that grow roses. This is the second largest rose producer in the world. About 4 aircrafts full of roses go from Nairobi airport to Amsterdam every day morning. And they get a very premium price for this rose because it is green roses, environmentally produced, friendly produce. Same thing if you see Jane over here in this picture, that's in Kenya again. They grow greenhouses and they use the hot water that's relatively hot, used to grow tomatoes, capsicum, etc. Now you see here, that same water goes into this pond, which is actually an aquaculture pond. So what happens is, after the steam is produced, the local stakeholders get involved and they grow fishes in that pond, which likes to grow better because they like a little bit of sort of lukewarm temperatures. Now, one of the biggest things currently is lithium. I'm sure some of you all have got your Teslas or one of your EV vehicles. If not, you all will be buying soon. Now, geothermal brine, especially in some of the areas in the world, has a very big component of lithium, either in the form of lithium chloride, lithium hydroxide. So now, I almost get calls every week. Sam, we want to build a lithium project in the Salton Sea. So before it used to be power with lithium, but now because of the money that we almost call lithium as white gold, because of that, people are now looking at producing lithium and using power that is produced to run the power plants and the captive production. This is a big thing now, lithium. And last of it, you all might have heard about, carbon. Everybody's trying to make their carbon footprint smaller. So here, actually, what they do is they use the carbon to pump it back into the ground. And actually, I was just reading today, they are now using the carbon, CO2, carbon dioxide, to refine it to make it food grade for things like your Coke that you all might be drinking has some carbonated CO2. They're using that. Also, they are using that for medical facilities to cool things that can be transported long away. One of the other big things that I have seen currently in Colombia that I was there last week is coffee drying and some of the other fruits, especially in Dominica. They used to not have much of heating and cooling. Now we are using geothermal heat to heat and cool. Plus, they're using it for dehydration. Some of the places in the world, there's a lot of fruit produced, but because of the facilities not being there to, utilize this fruit properly, you go to any of the local fruit markets, at the end of the day, you see a lot of fruit being wasted. Now, what they do, they take these fruits back to the dehydration plant, dehydrate it so that you can have mangoes in non-mango season. These are things that are being really pushed upon now, and they actually help in two things: adding value, plus there's a lot of stakeholder engagement. Why is this very important? I'm sure in the US, you all might not have seen this much, but in different parts of the world, stakeholder engagement is very important because they help these projects go together. If you cannot convince the people in that area that you're going to do good to them, they might even put a stop to the project. Plus, there's a lot of economic value where I'm sure if you go to the supermarkets now, you see the organic food is much expensive than the normal produced You just look for bananas. If you go and look for bananas, your normal bananas are probably 50 cents a pound. And the moment you add organic to that, you're paying a premium to eat the same banana. That's what we are looking over here and being used, the heat being used for different purposes. I will close there for now. And this is the last picture that you have that's one of the projects in Hawaii, where actually I was handling the lava. This is one of the lava flows that is there still growing around and produces, that's where we produce power of about 38 megawatts from that lava field. Thank you very much for your time. Appreciate that.
Yeah.
Open for discussions and any questions.
Thank you very much, sir. No questions?
Yeah, I have a question.
Feel free.
Come close.
Hello, good afternoon, Dr. Abraham. Thank you very much
Yes,
for the presentation.
you're welcome.
My question is, you mentioned the casing is getting bigger and bigger due to the temperature, and now
Casing is stretching.
yeah.
Mostly it is, yes.
Yeah, but the thing is, how do you handle this? I mean, like, when do you do cementing job? So how much time do you need, like, to cement this casing? And maybe it's going to squeeze or shrink while you are doing cementing job. Is it the case, or?
No, normally it is not doing. Okay, thank you for that question. Go ahead. You have completed your question?
No, it's my question. That's it.
Okay, fine. So what we do is, see, when you are doing the cementing job or when you're drilling, the temperature of the well has not reached its peak. Okay, there you are still able to, and what we do is, even while cementing, we do circulate a fluid a lot more of time. So normally if you look at oil and gas wells, we do one circulation, cool the well down, and I can do cementing. But some of the geothermal wells, when we are doing especially that last deepest casing, I would make sure to circulate the well properly to cool the well down before I do the cement job. That's number one. Number two, if you saw the foam cement, why we use that foam cement is that cement has bubbles of nitrogen in them, and they make the foam more elastic. So if the casing tends to have a little bit of expansion or contraction, that foam cement helps with that. Now, the main thing comes in is after you have done drilling. You remember the picture that I was showing where we were standing next to the steam flowing? After that, when you have stopped pumping any more fluid down into the wellbore, that is the time when the casing starts heating up. So what we do, for example, when we do our annual maintenance on these wells, where we have to close the well in and let the temperature cool down before you can do any work. So what we do there, we do a very stepwise cooling down of the well using nitrogen before I can shut it in. So what happens? The thermal stresses that I would have had, it is like very simple. You can take, you take a frying pan, you put water in that and you heat it. And the moment you take and put it under that will somewhere have a problem. So same thing happens. So rather than drastically cooling this casing down very quickly, we actually almost have taken sometimes 5 to 6 hours to cool this casing down properly, so that thermal stresses are reduced as much as we can. Still there are, I'm not saying no, but we try to reduce it. Now, after we do the workover, we do the same thing in the reverse manner. So what we do, okay, I've done my workover, cleaned out the well, everything is ready to go. I use nitrogen again to bring this well slowly back up. So it slowly builds up temperature. I try to use the nitrogen to lift the well. And as the well starts flowing, I reduce the amount of nitrogen I'm pumping. So in about 2 to 3 hours time, the well is back online. And the amount of stress that would have happened on the casing, if I had just turned it on, reduces and helps us to reduce the risk of any casing damage.
So should we expect the change of the position of the master valve? So before production and after production, I mean, like geothermal.
There is sometimes, yes.
For example,
yes.
you see master valve is here, and probably after 1 week, you see that it's just moved up.
So what happens is after it has, so you turn the well on, so it has gone from about, say it has come to a certain equilibrium, okay, 300 degrees, that's a flowing temperature. At that point, then the master valve will not move much. So we normally have, when on these master valves also, we've got some supports that help this master valve to grow a little bit back and forth. so that, and we've got some expansion joints even on that master valve. So where you saw that expansion spool, this is actually an expansion joint over there that allows the innermost casing to grow inside so that the master valve is not picked up too much. But that is also something that we take into consideration.
So do we have same type of connections for the casings too?
Yes, casings we are trying nowadays. Okay, now there is one of the new research that is going on. They are trying to use casings that will be helpful. So one of the things here is, if you see the casing that I showed you over here, so normally this casings, they normally, if you see your normal buttress thread casings, they almost touch each other. Whereas if you see, this is a special type of 10RS hydral casing connection. You see this one rests on a shoulder so that it cannot go down or go up past that point. Whereas if it was buttress, it would almost sometimes run into each other and cross problems. But here you see, this is the shoulder to which it can grow both ways and will stop over there.
Okay, thank you.
Any other questions? Thanks for that. That's a good question.
Thank you.
Okay. I have a question. Can you expand a little bit how to, okay, the difference between a well control, how to control a blowout event in geothermal, because that is mostly related to temperature and
yes,
to cooling down the well.
Yes. Thank you. I think you guys have been thinking about it. That's pretty good. So what we do is, when we talk in terms of, and do you all know about normal well control in oil and gas wells? Have you heard of that?
Yes, sir.
So you normally have a wait and wait method or a driller's method. Okay. That is all possible when the temperature is not that big an issue. In geothermal, our biggest problem is temperature. So what we do in terms of geothermal wells is, once I have been able to sort of control, once a well kicks in, I close my BOPs. The next thing I do is I just pump water down the well bore, both down the drill string as well as down the annulus. So that is our only, we call it bullheading, and that is the reason why we always insist on at least having 3 pumps. Because sometimes what happens is, if there's only 2 pumps and I've got 1 pump on the drill string and 1 pump on the backside on the annulus, and if one of the pump fails, the well can continue to come alive. So that is why we always have a spare pump, to make sure that we call it bullheading. So I will pump cold water down the well drill string and down the annulus at the same time to be able to kill it. And sometimes you have to keep pumping it for a long time, because the well takes some time to cool down and then go back into vacuum. But that is our main way of controlling this well, bullet down. But that's why you also have 2 things. Always have almost 2000 liters per minute of water available. That is your only weapon to control a geothermal well.
Yeah, and the 3 pumps, that is also essential. And thank you for that point. That is a very good point.
Yes, because that is a place where we have seen problems where people have tried, if I only contract a rig with 2 pumps, it's cheaper. No, there is that backup. Okay, I'll tell you one more thing, that point over here. Sometimes in some of these places, as I told, Hawaii or in Kenya, my nearest point is of any oil field supplies is Dubai. Again, 14 days distance. So what I do as a project manager, as a drilling manager, I carry something called backup of a backup. For those who are not common with that term, how many spare tires do you have in your car? You have only 1 spare tire. If it was me, if I'm going on a really long journey, I would carry the second spare tire. So sometimes the finance manager asks me, Sam, why the hell do you need 2 spares? No, I said, I do not mind paying $50 extra for a spare tire rather than waiting 5 days to get this casing or this spare in. So many a times in remote locations like these, we always carry some very essential spares and backup of those spares. We can avoid problems of waiting 14 days. And as you said, $100,000 a day, that is $1.4 million. Whereas I can keep the same spare for about $50,000 for the whole month.
Thank you.
Any other questions?
As
Hi,
always, great having you. I have a
Thank
question. You touched a little bit
Please.
on elastomer. I remember, we were doing some research on elastomers, and
Yes.
we observed that temperature has a very significant impact on, them
Yes.
blistering and, damaging them.
Yes.
I was wondering if geothermal industry have moved towards, having, let's say improve elastomer, or, how do they, control that?
Right. Thank you for that question. So I should have touched. Okay, that is a good thing. So two things there. One is elastomers. They have gone, now they're trying the Vitron or the Vitron, the type, which has got a higher temperature limit on elastomer activity. That's number one. Then what we do is also while drilling, especially when we have got this high, I was talking of directional drilling tools, which have got elastomers in them, which are over, they cannot take over more than 175. So we make sure we've got mud coolers. You might have seen, I don't know whether I skipped that. There are mud coolers that we use on the rig site. What their main purpose is to keep the well cool as much as you can while drilling. Okay. We actually, so this white thing that you see over there, that's a mud cooler. That actually is a proper mud cooler that can almost decrease temperature by about 30 degrees centigrade through one. So some of these wells that we have got high temperatures, we have 3 of them working in tandem just to keep the temperature below that limit. Now, the third thing is that some of the casings, etc., where we are having elastomers, now they're trying metal to metal seals, which again gives us a little bit more of temperature capability to work with, because the metals are used, in helping to take that temperature thermal stress out of it. But still, that is a big challenge even now. And Forge project also is quite involved in that, where they're trying to see what can I have to increase the temperature limits of these type of tools. Because as Professor Saeed was telling, for all the students, these are one of the most important things in the whole drill string. You can have a drill string very good, one elastomer that is leaking, that is the end of that drill string. Just one elastomer, rest everything. And this is applicable, I work a lot with the flight industry because of the turbines. Everything on that aircraft will be perfectly fine, but one O-ring can actually cause the aircraft to come down. Same thing in terms of oil and gas or geothermal wells. One O-ring that is not correctly put can cause damage. So that is why we have to, again, elastomers, we make sure of one thing. After it is run one time, we do not rerun that in the wellbore. We always put a new elastomer, even if it looks the best. I always make sure to change it before I run it down the next time.
Sam, I'm sure you probably know this, the 1986, the Challenger, there was a
Yes.
book that
Yes.
failed because of, the elastomers. So that was a
Yes.
very good point,
Because this is now, for those who are, I work for Sandia National Lab now, and we have actually developed a system on how to avoid problems. And I did not know this. And this was actually an outcome of that same Challenger accident, that they came up with something that, they have set up a whole testing setup. And one of the most important things in that testing setup is that, for example, if there is a part that's being tested, Mr. Saeed, who is the specialist on that, has the whole responsibility to test that. Even if it is done 1,000 times, it is only Mr. Saeed who's going to test it, nobody else, because he knows, and responsibility goes back on him. So it's both a responsibility as well as a duty to make sure that thing is done properly. So this is one of the things that I learned from that unknowingly. And now this is being applied in Sandia National Lab as I'm doing this project of making sure repeatability of testing is the most important thing, and responsibility of doing that.
Exactly.
Yes.
Sometimes you have students, join us, and they cannot repeat the previous students' work, so
Yes.
I have seen that as an important,
and again, one more thing as a part of that. If you once, I'm sure you engineers will be going to the field sometime. One thing I've learned, again, out of my personal experience, if you have got something on the rig side, you want to go and see whether that is there. Do not trust somebody else. You go, I have this habit, go and touch and feel that equipment. Okay, Professor Saeed asked me, Sam, go to the field and check if this casing shoe is there. I will personally drive up, touch it and tell, okay, it is there. But I do not take somebody's word as long as, or Nowadays, you've got the ability that somebody can take me a picture and send it back. Okay, now I know it is there. Otherwise, touch it, feel it, make sure it is there. Do not take chances with that.
Good point. Yeah. Thank you, Sam. It was a really informative lecture you had.
Thank you very much. And if you students have any questions, I'm on LinkedIn, or I think you all have, Orkan has got my email address also. You all have any questions, if I can be of help, feel free to reach out anytime. And thanks, Professor Saeed, for once again giving this opportunity to discuss with your students, not teach them,
Yeah,
discuss with them.
perfect. We'd like to have you every year, Sam. It's a pleasure. Thank you so much.
My pleasure. Take care. You guys have a nice afternoon.
Yeah.
And
Sure.
catch up soon.
You the same. Thank you.
Take care.
Thank you.
Bye for now.
Bye for now.